All right, so we're talking Markov chains and stuff. Okay, so here's a brief recap of Wednesday. Let's just kind of review. Why is this flickering? Okay, recap of Wednesday. We said, we could have some kind of. We just looked at a two-state kind of Markov chain, and we said we can go from A to B. We can also go back onto itself. We can remain at the same state, and we said we got some transition matrix, which we'll call P. This is and this top corner would be the transition from A going to A, and then over here we would have the transition probability of A going to B. Down here we have the transition probability of B going to A, and the probability of going from B to B. Okay. Now if I said I want to draw an arrow, but let A be state 1 and let B be state 2. Then we can label our probabilities as such. Okay. And we have the property, P has the property where the row sums equal 1, right? All right, and I said that if you've got some state that regardless of the initial state, so if the chain is aperiodic, what does it mean to be aperiodic? That the states can kind of show up at kind of any time interval type of thing, or it's not A's only show up on the evens or something like that, and that will happen if at least one of the elements can go back to itself. Okay, so if the chain is aperiodic and irreducible, what does it mean to be irreducible? It means you can reach any of the other states from any state. Okay, so all the states basically can reach each other, given you enough time. Okay, then the chain will eventually converge to its stationary distribution. Stationary or equilibrium distribution, okay? And this is regardless of the initial state. So no matter what the initial state looks like, if you let the chain run long enough, it will converge to its equilibrium distribution. Okay? And the stationary distribution is the distribution where basically the number entering the state is equal to the number leaving the state for all states. So when that happens, then we've reached equilibrium, or our stationary distribution, which means the number leaving state A is equal to the number coming into state A, and the number coming into state B is equal to the number leaving state B. And if you have more than 2 states, if you got like 10 states, you're at the stationary distribution when all the numbers coming in is equal to the numbers going out. Okay. And here's this little website that kind of illustrates this with eigenvectors and whatever. All right, so here is a diagram representing, apparently there's only 2 states, California and New York, which we'll consider here. And we'll start off with the population of California being 38.33 and the population of New York being 19.65 million. And we're going to say if you're in California, there's a 10% probability of going to New York. And if you're in New York, there's a 30% probability you'll come to California, okay? And we can mess around with these numbers. And so what will happen is here, I think we've got like each dot represents kind of like 1 million people. And what we will see when I hover over this is that 10% of the blue dots will move over to New York, and 30% of the yellow dots will move to California, okay? And this will happen, this will repeat. So some of the blue dots go to New York, and when this happens, it changes the size of the circle, and then, and eventually, we reach a point where the number leaving blue is equal to the number of yellow coming in, okay? And so the amount leaving is equal to the amount coming in, and this happens for both states, okay? And we can modify this so that we can start off with everyone at New York, okay? And if we start with everyone at New York, then 30% of New York will come to California, and then in the next cycle, 10% of those in California will go to New York, and 30% of New York will come to California, okay? So when we do this, about 30% come and become California, and about 10% of those go back to New York, and we see that it keeps kind of switching around until we reach a point where the same number that leave enter, okay? And so even though in the beginning we started off with everyone in New York, after running a few iterations, it steadies out, okay? So it's still, the numbers leaving are not equal to the numbers coming in, but we're getting closer to that, and it looks like, right around here, it seems like the number that are leaving is equal to the number coming in, right? And if I change the initial conditions so that everyone is in California, we'll see the same kind of thing, okay? Some go away, and we'll, and I think right here we got just about the same number. Is that 7? Yeah, 7 leaving, 7 coming in type of thing, okay? And they end up having the kind of the same distribution. And we can change with this thing. We can modify. We can say if you're in California, 80% probability of going to New York, and if you're in New York, 30% probability of coming to California. So we can kind of modify these transition probabilities. And so here, we're going to start in California, And then 80% of California will go to New York, only 20% will stay. So there you go. And then now we've reached kind of equilibrium, where the amount leaving is the amount coming in. Or, you know, we could change it around this way. Some go over here, and then, you know, 80% leave, so on and so forth. Okay, and what this whole page is about is it talks about how you know, the steady state can be found by finding the, you know, Markov, I'm sorry, the eigenvector. So it turns out, so it says here, it turns out that a matrix like A, whose entries are positive and whose columns, so in this case it will be, and the way we wrote our matrix is that the rows add up to 1. It's called the Markov Matrix, and it always has lambda equal to 1 as its largest eigenvalue, and that means there's a value, V, okay, such that A times V, or in this case we wrote it a little bit backwards, V times A is going to equal some, you know, 1 times V, and this will be the steady state. Okay, so this will be the eigenvector of our transition probability matrix. Okay. So I'll link to this page. This is a good one. Okay, so so our notation is just ever so slightly different from what that page is, but you know, if we write distribution and transition matrix as basically the current distribution, this is some vector basically V, and this will be times the transition probability matrix P, okay, and this will be our next distribution. Then effectively, if we reach a point where the current, this vector times the matrix is equal to the current vector, then that's going to be an eigenvector of the matrix, right? Okay, so we'll, you know, P, that's the property. The row sums equal 1, okay? And it will be, you know, the stationary distribution is the distribution where the current distribution times, you know, the matrix P is equal back to our current distribution. Okay, which means the current distribution, or I should say, the stationary distribution is not current, but where the stationary distribution times the transition matrix is equal to the stationary distribution. Is an eigenvector of the, technically it's the transpose of the transition matrix. And for the two-state case, if you have P11, P12, P21, and P22, then the stationary distribution pi will equal P21 over P12 plus P21, comma P12 over. Okay, so for example, I think we were looking at the case where we had 0.7, 0.3, 0.4, and 0.6 on Wednesday. We said, you know, transition probabilities of this matrix, and then our stationary distribution will be 0.4 over 0.4 plus 0.3, comma 0.3 over 0.4 plus 0.3, which ended up being 4/7 and 3/7. Okay, and that's how it works for the two-state case. Sorry, I don't know why the screen keeps flickering. All the connections here are connected, so. Okay. Are there any questions here? Is this okay? All right, and so so we have kind of this idea of Markov chains, and let me just step back and cover the big picture again. The big picture is that there's some distribution, and we want to understand the properties of the distribution, and we can't analyze the distribution directly, so instead we're going to settle to try to get a representative sample drawn from the distribution. Okay, so we want to draw a representative sample from some distribution. Okay, you know, to learn properties of this distribution. And it could be really hard to get a representative sample with the techniques that we have, okay? Could be hard, you know, or you know, because of sparsity. How do you spell sparsity? You know, very inefficient. Okay, and so you know, if we're able to design a Markov chain where the stationary distribution is equal to the target distribution, then we can simply draw values according to the transition probabilities. Okay. Okay, so the goal is to get a Markov chain where the stationary distribution of the Markov chain is equal to the target distribution, right? Because we want to get we have some distribution out there, and we're not able to sample from it directly. Like if we did rejection sampling, maybe it's very inefficient, or we can't do inverse CDF, or whatever it is, we can't draw a random sample from it directly. We can't analyze this thing directly. So, but we want to know, how can we get a representative sample? Okay. Well, the idea is we want to design a Markov chain so that the each state or each thing produced in the Markov chain will look like the target distribution. Okay, so a silly example is if our target distribution is A has probability 4/7 and B has probability 3/7. Okay, let's say for whatever reason we're not able to draw from this directly. Okay, like a random number device produces digits 0 through 9 or something. Okay, so let's say you've got a random digit device that produces values 0 through 9, and so you could do rejection sampling, but then that means you have to throw, anytime you get basically something 7, 8, or 9, you got to throw it away, and you're only using values 0 through 7 or something, or 0 through 6 or something. I mean, that's possible, but we're going to say, we can't so we won't draw from this directly. Instead, we'll use a Markov chain. Okay, and so if we run a chain with transition probabilities P equal to 0.7, 0.3, 0.4, 0.6, okay, then the chain that goes, A, B, A, B, B, A, B, whatever, etc., 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 will, so if we use this to generate our samples A and B, saying if I'm at A, I've got a 70% chance of drawing A again, or 30% chance of drawing B on the next turn, we'll have a distribution of 4/7, 3/7, after enough iterations. Is that okay? And so this is kind of the big picture idea, is we've got some target distribution over here, and in this case it's a discrete one, but it can be generalized to a continuous case, and we're going to say we can't get it directly by just doing rejection sampling, or we don't want to do rejection sampling because maybe it's very inefficient or something. So to kind of get a representative sample, we're going to run a Markov chain instead. Okay. All right, so let me introduce kind of our first Markov chain Monte Carlo algorithm, and this will be called the Metropolis algorithm. Okay, and I'm going to use the example in our textbook, Chapter 7, doing Bayesian data analysis. All right, and let's say we've got an island nation. So this is the example in our textbook. Excuse me. get like a drink of water or something. Got an island nation with 7 islands in a row. All right, so we got these 7 islands, and let's say there is a politician who wants to make campaign visits and hold these campaign events at the different islands, right? Okay, and we're going to say that he wants to visit each island in proportion to the population of the island. Okay, so the big islands that have lots of people, he wants to visit those lots of times. Small islands with few people, he still wants to visit them, but spend less time there. Okay, so the politician wants to visit and campaign at the different islands, but wants to spend time in proportion to the population of the island. All right, and this, in our contrived example, just to kind of make sure we can do this, we're going to say the politician does not know the population of all the islands, okay? Okay, which means, in other words, we can't sample directly. But what we are able to do is, we are able to call, the governor of the island of any one island and find its population. But for whatever reason, we can't learn all the islands at the same time, okay? All right. Us being, the creator of this example, we will say we know the populations of the islands, okay? So we know the populations of the island because we are making the example, right? Making up this example. All right, so for simplicity, we're going to just say island 1 has 1 million people. Island 2 is 2 million. Island 3 is 3 million, etc., 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 up until island 7 has 7 million. Okay, for a total of 28 million people. I think if you add up 10, 15, 21, 28, yeah. All right, is that okay? So so each island basically has whatever island number it is, that's how many people live there. Okay, this is going to be how the algorithm will run, okay? This is the algorithm the politician will use. Okay, so he wakes up on some island we'll call theta, all right? And then we will flip a coin. I'll say he flips a coin, and if it is heads, he proposes going to the island to the right. Okay, so that would be theta plus 1. Okay, and if it's tails, he proposes going left, which will be island theta minus 1. Okay, so we're currently at island theta, so if we're at island 4, and if we flip heads, we would propose going to island 5. And if we're at island 4 and we flip tails, we would propose going to island 3. Okay, simple enough. Now, if that was the only step, then we would end up, kind of visiting all the islands with equal probability in the long run, right? Because we would either go to the right or go to the left, go to the right or go to the left, something like that. Okay. So this is what we will do is that if the proposed island has a larger population, so whatever island we propose, we'll call that governor and find out the population. So if the proposed island has a larger population, we will go visit that island, okay? We'll go to that island. Okay? On the other hand, if the proposed island has a smaller population than our current island, we might go or we might not go. Okay, and we will go with probability, basically proposed island population divided by current island population. Okay. So basically, you draw like a random uniform from 0 to 1, and if it's smaller than this number, you'll go to the proposed island, and if it's bigger, you don't. Okay, so basically. Less than the ratio, go to proposed island. And if it is greater than the ratio, stay put and spend another day at the current island. And that's what we'll do, okay? So the politician will propose, say, I'm currently at island 4, we flip a coin, and let's say it lands heads, and it says, all right, let's propose island 5. And we go, oh, island 5 is bigger than island 4, we will go there for sure, okay? on the other hand, if we wake up on island 4, we flip a coin and we get tails, we'll say, oh, it's proposing going to island 3. And then we say, well, island 3 is a smaller island than this one, so maybe I don't want to go. Okay, and we say, all right, well then let's draw a random number between 0 and 1, and we'll compare it to this ratio of island 3 has a population of 3 million and island 4 has a population of 4 million. So we'll go to island 3 with a probability of 75%, and if not, we'll stay put with a probability of 25%. Okay, and that's if we flip tails. Does that kind of make sense? All right, so let's just kind of show what this might look like. Okay, so let's say our initial state is we wake up on island 4. So our distribution now at time 0 is 0, 0, 0, 1, 0, 0, 0. Okay, so this represents the different islands. So right now our distribution is we are on island 4. Okay. All right, let's say at the next step, where will we be? Okay. So we have a few possibilities, right? So if I flip, if I get heads, this is probability equal to 0.5. I propose island 5. Okay, and if I propose island 5, I will for sure go to island 5 because, and then I will for sure go to island 5 because island 5 has a larger population. Okay. So we will end up at island 5 with a probability of 0.5. Okay. All right. On the other hand, I could flip tails with probability equal to 0.5. Okay, so we propose island 3. Okay, island 3 is smaller than island 4, so maybe I'll go, maybe I won't go. Okay, so I will go to island 3 with probability equal to island 3 population divided by island 4 population, my current island. So this will be 3 over 4.75. Okay, so the total probability, which means I won't go with probability 1 over 4 or 0.25. So I won't go means I stay at 4 with probability 0.25. Is that okay? All right, and then so the total probability of going to island 3 is going to equal 0.5. I have to first flip tails, and then times 0.75. And then the total probability of remaining at island 4 is equal to 0.45 times the probability of staying, 0.25, 0.125. Okay, and so my distribution at the next step will be going to be 0, 0, 0.12, 0.375, 0.125, 0.5, 0, and 0. Is that okay? And this row here, this is equivalent to the fourth row in our transition probability matrix, right? Is that okay? So I'll start kind of filling this out, and I'll leave the rest for you to do. So we can build a transition matrix for all 7 islands. So we'll start off with kind of from island 1, 2, 3, 4, 5, 6, 7, and we may propose going to island 1, 2, 3, 4, 5, 6, 7. Okay, and we said from island 4, we will go to island 1 with probability 0, we'll go to island 2 with probability 0, we'll end up at island 3 with probability 3.375, 0.125, 0.5, 0, and 0. Okay. All right, let's say we start off at island 1, okay? If we're at island 1, because we're only proposing islands that are adjacent to us, so there's no possibility of ending up at islands 3, 4, 5, 6, or 7, okay? And if we're at island 1, I could flip heads, and if I flip heads, I would go to island 2 with probability 0.5. So this is probability of flipping heads and proposing island 2, and then we go to island 2. So that will happen for sure, right? Okay, well, we know the row has to add up to 1, so we already know that this answer has to be 0.5, but let's think about that. Okay, so let's say for this to happen, I would have to probability of flipping tails is 0.5, okay? And then what would end up happening is we propose island 0, and we say island 0 does not exist. It has a population of 0, okay? So we go to island 0, with probability equal to 0, which means we remain at island 1 with probability equal to 1, okay, times the 0.5. So our total probability of staying at island 1 would be 0.5. Is that okay? All right, let's look at this bottom row for island 7. So from island 7, I can't go to island 0, 1, 2, islands. I can't go to 1, 2, 3, 4, or 5. I might end up going to island 6. Okay, so let's figure out what's the probability of going to island 6. What has to happen? So we first have to flip what? So we flip tails with probability equal to 0.5. Okay? So we flip tails with probability 0.5, and that means we propose island 6. Okay? And we check the population, all right? Island 6 has a smaller population, so we go to island 6 with probability what? Equal to the population of island 6, which will be 6 over our current island population 7. So we'll go to island 6 with probability 6 over 7. So the total probability of going to island 6 will equal basically 1/2 times 6/7. So we have 6 over 14, or 3/7. Okay. All right, and then so what's the probability over here of staying at island 7? Okay, so this is going to equal basically the probability of proposing island 8 and not going, which is going to be 0.5, plus the probability of proposing island 6 and not going, okay, which is going to be the probability of 0.5 times, we would go to island 6 with probability 6/7 once we propose it, and we would stay put with probability 1/7 after we propose it. So this ends up being 0.5 plus 0.5 times 1/7, so this ends up being 8 over 14, or 4/7, okay? And then in your next homework assignment, I'll have you fill out the rest of this transition matrix, which isn't too hard to do, okay? All right, we'll end there. Have a great weekend.